Now, force between plates of a parallel plate capacitor. So basically, how much force do these two plates apply on each other? Since one is positive, one is negative, they will definitely attract each other. So we just have to find the magnitude of the force. So what we are saying is that if we have to find the force on a single charge, point charge, then we say that force is nothing but Q into E. What is E? E is the field in this region or over here due to other charges. So similarly, I am finding force on this plate. So I am simply saying it is nothing but charge into electric field over here, or we will say the field over here into discharge, and that charge I am simply writing it is dq. Okay, so electric field, first is what is the electric field. So if electric field over here due to this plate we are checking, then this is just sigma by 2 epsilon naught. Due to both in the between there is the equivalent electric field is sigma by epsilon naught. Due to single it is simply sigma by 2 epsilon naught. It is in this direction, but since it is negative charge, the force will be in this direction. So now if someone is saying that what is the force, we will say force is nothing but charge, that charge dq into electric field E. What is that charge dq? If we are talking about a very small area ds over here on which this dq charge is lying for the plate, then we will say this is sigma times ds times the electric field which is sigma by 2 epsilon naught, and that gives me the sigma square by 2 epsilon naught and ds. This is my df. If I have to get the total force, then what can I do? I can simply integrate this entire thing and I can integrate my df, and once I integrate, see sigma square is a constant quantity, 2 epsilon naught is a constant quantity, then it is integration ds which gives me the total area of the plate, because ds was small area on this plate. When you integrate you get total area of the plate, and that is my total force. If this area goes over here, then we get force per unit area, and that is sigma square by 2 epsilon naught, and this is the expression which you should remember, that they do attract each other. These two plates do attract with each other with a force of sigma square by 2 epsilon naught per unit area. So we just seen that this plate is being attracted by the other plate. So the first plate, the negative plate, will also be attracting the positive plate by the Newton's third law of action and reaction. That can be said, or the same derivation can be done again for the force on the other, but it is equal in magnitude and it is the attractive force on both the plates due to each other. So answer is that force per unit area is sigma square by 2 epsilon naught. So this is what we need to remember, and this is what is which is important. Now next is energy stored in a capacitor. So the energy stored in a capacitor is equal to the work done. Work done in what? Work done in to charge it. So basically we have two plates. Let us say that we have two plates, like one plate is over here, other plate is over here. What I am going to do is I am going to give it charge Q. So there is already charge Q and plus Q and minus Q. So there is already charge on this plus Q and minus Q. What I am going to do is I am going to give a further charge of dq on this and a charge of minus dq on this. So how much is the work done? So work done is basically, and let the potential difference between them be V. So I'll say the work done is nothing but V times delta Q, or see generally it is Q times delta V, but here the charge is changing, potential we are keeping same. So we are just giving the charge, we are maintaining this potential. So it is basically V times dq, and that V is what? V can be written as, since Q is equal to CV, and hence we can write that V is nothing but Q by C. So I just replaced it over V to be Q by C, and dq I can simply integrate and get the total work done. So when we integrate that, what we get is this term becomes integration, so Q by C, so 1 by C comes out as it is, and this Q is Q square by 2, and limit is charging from 0 to Q. So eventually you get Q square by 2C. There are some more variation like this. So what are these variation is, Q can be written as CV. So we can write that Q square by 2C, that is my energy of a capacitor, or to be precise, potential energy, or you can also say work done in charging it. So that is nothing but C square V square by 2C. So 1C gets cancelled and we get half CV square. And this is my this expression. When I replace this C, so I can write U is equal to Q square by 2C and C is what? Q by V. So I am replacing that Q by V. So this V comes here, 1Q gets cancelled and we get QV by 2 and this is my this expression. So there are three expressions for total work done to charge a capacitor, or the total energy stored in a capacitor is given by Q square by 2C, QV by 2 or half CV square. There are three expressions for it and eventually all three gives you the same. If you want to remember just one, you can remember. You just need to remember that Q is equal to CV is another equation. And if you use those, you can get the other expression as well. Next is we are talking about energy only. But now we are going to specifically derive a new thing called energy density. So first, I know that this is the capacitance and V can be written as E and E into D, because V is electric field is nothing but V by D, right? V is the potential difference between the plates and D is the distance of separation between them. Now we know that U is half CV square. I'm just replacing my capacitance as epsilon naught A by D and the V as nothing but E into D. There is a V square, so ED whole square. Once I do that, this is half 1 of the D gets cancelled from here and we get single D, and this area is again with this is E square, right? So this is what we get, that half epsilon naught E square times AD. Now what is A into D? These are our two plates separated by a distance D. Each one is having an area of cross section A, and then we are looking at, when we are looking at A into D, this is nothing but the volume or space between the plates. So this is entire volume. So this is volume and this is my potential energy. So potential energy can also be written as half epsilon naught E square times the volume of the capacitor. If this AD or volume gets divided by U, then we get the total energy per unit volume, and that is what is defined as energy density or energy per unit volume. So this is defined as total U divided by total volume. Volume is AD, this AD comes basically in the denominator of that, and eventually we get U by AD, and that is our energy density, generally denoted by small u, is nothing but half epsilon naught E square. So this is the energy per unit volume or energy density for a capacitor. So how is this useful? So this formula is useful not just for capacitor chapter. See, we are going to use that for electrostatic also, because if this is a capacitor, then in between two capacitor, we know that there is a uniform electric field which exists from starting from positive plate to the negative plate. So I am saying in this volume, if we see, then we just have a uniform electric field. So we can say this entire energy density or energy per unit volume is also the energy stored for the electric field or for a uniform electric field for a certain space or for a per unit volume. So this is also the electric field energy per unit volume of it. So if we know that this is not a capacitor, we just know that it is a uniform electric field. There is V volume, which we are talking about. Capital V is the volume, and there exists a uniform electric field. How much energy is trapped in this V volume space? Then I'll say half epsilon naught E square is the energy per unit volume times the V volume, and that is the total energy which is trapped in this much of space. Now that space can be in the middle of the capacitor or can be part of the uniform electric field. That does not really matter. Now next is a question. This question says that a parallel plate air capacitor is made using two plates. Both the plates are 0.1 meter square in area and spaced 1 centimeter apart. Now it is connected to a 100-volt battery. They are asking what is the capacitance. For capacitance, I am going with the original formula epsilon naught A by D. I am calling this original capacitance as C naught. What are the values? Epsilon naught value you should remember 8.85 into 10 raised to power minus 12. The area of the plates is mentioned over here. is mentioned over here, and this is 0.1 meter square divided by the distance. Distance is 1 centimeter, and 1 centimeter is 1 into 10 raised to power minus 2. When we solve this entire thing, we get capacitance as 8.85 into 10 raised to power minus 12. So this is minus 10 and then minus 11. And this is farad because we have used all SI units only. So this is our original capacitance, 8.85 into 10 raised to power minus 11 farad. The same question is asking what is the charge on each plate. So charge on each plate, I am just applying this formula, Q is equal to CV. And what is C? We just found it out, 8.85 into 10 raised to power minus 11 farad. And what is V? V is the potential difference between the plates, which is the potential difference applied by the battery, that is 100 volt. And that gives me 8.85 into 10 raised to power minus 9. And this is charge, so it is coulomb. And this is again SI unit because we used everything as SI units. Now next is what is the energy stored in the capacitor. So let us say that energy stored in the capacitor is E naught. So we can apply all the formulas. We can apply half CV square, or we can apply Q square by 2C. I'm using C naught, or I can apply QV by 2. Now, I am going to choose this one because I have capacitance, I have potential difference. You can choose these two as well, as we have already found charge also in the previous question. So it is half, C naught is 8.85 into 10 raised to power minus 11 into V naught squared, so 10 raised to power 4. That gives me 4.425 into 10 raised to power minus 7. And this is joules. So this is the energy stored in the capacitor. Now next part is saying that what is the electric field in between the plates. So electric field, E can simply be written as the total V by D. We already have the potential difference as the battery has been applied across two of the parallel plates. And so it is 100 volt and distance is how much? 1 centimeter. So 0.1. 1 into 10 raised to power minus 2 meters, and eventually that will give us 10 raised to power 4 volt per meter, or you can also write Newton per coulomb. It's your choice. So this is the electric field in between the plates. Now the last part says that if the battery is disconnected, first we are disconnecting the battery. So this capacitor was connected to a battery. Once I disconnect the battery, what will happen? The 100 volt potential difference which this battery was maintaining will not be maintained. What will happen is the charge, whatever charge battery has given, now the charge of each plate is fixed. Now when you are doing the separation, when you are increasing the separation, okay, separation becomes 2 centimeter. So they are pulled apart to a separation of 2 centimeter. What are the answers to above part? So what happens to each of the quantity? So original capacitance is epsilon naught A by D. And we know that when this distance increases twice, this capacitance happens to be half. So the new capacitance is original capacitance by 2. So this is what happens with capacitance. Next thing is what happens with energy. So energy was Q square by 2C. So charge is not changing because charge can't flow now anymore, and C is becoming half. So if this becomes half, this becomes twice. So the new energy is original energy into 2. What happens with electric field? E is V by D. But if I use this formula, then the V is, I need to get what is happening with potential difference. So since Q is equal to CV, the charge is same. This is becoming half. This should become twice. So the E dash, the new electric field is 2V, that is the new potential by new distance, which is 2 times D. So it is same as the original electric field. So nothing is happening with electric field. Capacitance is becoming half, potential energy is becoming twice. Now let us have a look at the next question. So this question says that the plate separation in a parallel plate capacitor is D and the plate area is capital A. Now if it is charged to a V voltage, then and the battery is disconnected, then work done in increasing the plate separation to 2D will be what? So we have 4 options. So now let us again understand. It's just same as the previous problem. When we have already charged to V volt, what will happen? This plate will get a charge Q. This will get a charge minus Q, and that Q will be nothing but CV. What is C? C is nothing but epsilon naught A by D. So this is like old or original capacitance into V. This is my charge on each plate. Now if I separate them and it is disconnected to the battery, then basically this charge does not have any option to change. So the charge on this plate will remain Q and the charge on this plate will remain negative Q. So charge will remain same, that is fixed. It just the separation is becoming twice. So then when this separation becomes 2D, charge is still Q and minus Q on them. So they are asking that what is the work done? So I am saying work done will be whatever is the increase or decrease in potential energy. So whatever the change in energy, that will be the work done. So what is the energy over here? Energy over here is half CV square. This is the energy, initial energy of the capacitor. What is the energy over here? It is half CV square, but C itself is what? See, when you are making the distance twice, so C is becoming C by 2. So the capacitance is now C by 2. What about the potential? So potential is also changing. So it is better that we use the formula Q square by 2C, because we know that it is the charge which is remaining same, right? So I am going to use the formula Q square by 2C rather than this, so that there is a lesser confusion. So this is Q square by 2C, C naught. And what about this? This is again Q square by 2 and new capacitance, which is basically C naught by 2. The capacitance becomes half. So now this is gone, and as we can see, this is Q square by C naught. This is Q square by 2C naught. So this energy is half. So initial energy is less, final energy is more. So it's an increase in potential energy. So we are doing work on this, and that is what is being asked. So work done is nothing but increase in potential energy, and that is Q square by C naught minus Q square by 2C naught, and eventually answer is Q square by 2C naught. Now if we see our option, no such option has been given. So we just need to write the value of Q, because and C naught also. So we need to substitute those two values. So what is Q square by 2C naught? Let's just have a look. So Q is nothing but this, and square of this, epsilon square A square V square by D square. And 2, what about C naught? Epsilon naught A by D. So this D is over here. Now just cancel out whatever you can. Epsilon naught A and 1 of the D. So it is half, 1 by 2 is half, epsilon naught A by D V square. So this is the correct option which we are getting. So this option is the correct. No other option matches, hence this is the correct answer. Or we can say this is the increase in potential energy, which is the work done by us on the capacitor. Like work done in increasing the plate separation from D to 2D.